Okay, so today I'm going to start the discussion on a special type of continuous probability distribution. And you already know that discrete probability distributions can have various forms, like as we discussed in our class, that binomial probability is a kind of discrete probability law, and Poisson probability is a kind of discrete probability law. The most important continuous probability distribution is the following. It is called normal distribution. The most important distribution in theory of statistics. Normal distribution actually can occur in every phase of a statistical survey. And the beauty of the normal distribution is that if we keep on increasing the sample size, then almost every probability distribution can tend to follow the normal distribution. I mean, in other words, if I'm going to increase my sample size, almost every probabilistic distribution tend to follow normal distribution. Normal distribution can also be treated as a special case of binomial distribution. For example, if you know that in binomial distribution, the parameter is small n and small p, where small n is the number of experiment and small p is the probability of success. Okay, and as you know that when n tends to infinity, that is, we are not sure about how many times we must repeat the experiment, repeat our observation, and its corresponding probability of success is very small, too small, that it tends towards zero, then binomial distribution actually follow the Poisson law. We already know this particular result. This is number one. But if your sample size or your observation or your experiment tends to infinity, that means you do not know how many times you are going to repeat your experiment, but your probability of success, P, is not actually tending towards zero. That means P is not too small. P is not too small. P is having some sort of significant value. Then binomial probability law tends to follow normal probability distribution. So this is the difference between these two limiting criteria. In this particular criteria, in number one, discrete probability tends to follow discrete probability. But in this second part, the discrete probability tends to follow a continuous probability. And it is very quite, I mean, amazing. Okay, so for example, if you have a statistical data, and if you want to plot the data in the following manner, in the form of a histogram, and suppose you are getting figures like this, probably you know how to draw the histogram. Okay, and you are getting figures like this, as I'm showing you. Okay, a quite symmetric figure, but since I'm drawing it manually by my hand, probably it is because I'm not very good in drawing. This is this kind of histogram if you get, and then after this, if you keep on increasing your number of observations and you consider these infinite strips, okay, like this, as many times as you can, you are going to repeat your experiment. And if you get a thing like this, a structure like this, at a certain point of time, what you will feel that you will not be able to differentiate between the two rectangular strips. And after if you keep on increasing, still if you keep on increasing, after a certain point of time, you will see that this particular figure will look like the following figure. It will be like this. Okay, so this will happen, this particular phase will happen when your n is tending towards infinity. Infinity here doesn't mean, because infinity is an abstract quantity and nobody can reach infinity in the finite lifespan. Here infinity actually means that we are not sure about how many times we are going to repeat our experiment. So if you keep repeating your experiment, you will find that your shape of your histogram will take the following shape. It will be symmetric. If you draw a line like this in the middle, the left hand side portion and the right hand side portion will be symmetric, means the left hand side portion will contain 50% of the total data, right hand side will contain 50% of the total data, so that the entire thing, entire curve contains 100% of the data. So it is a symmetric curve and it looks like bell, and therefore normal curves are often called bell curves. They are called bell curves and they are very important. They are very important. So we are going to discuss the properties of these bell curves, of this type of curves over here. First of all, we are going to learn about the probability formula or probability law which the random variable is going to follow. Then we are going to learn the other properties of the normal random variable, and then we will gradually go into the problems. And I hope that all of you must listen to me very attentively, and if you have any doubt in this particular portion of the statistics course, you will be having doubts and doubts in the subsequent cases, because the other modules in the subsequent modules are totally based upon this particular law. And I shall keep repeating I shall keep uttering the word normal law, normal distribution until the course finishes. So this is the most important, this is the most vital chapter of our syllabus. To begin with, let's discuss first of all, what is the probability law for this particular type of distribution. So suppose capital X is the normal variate. Suppose capital X is the normal variate. Variate is the synonym for variable. Then the probability law that capital X is going to follow will have the following mathematical expression. So we'll write it as the following: prob f of capital X, small x. This is the, notation I'm using over here. This notation, this type of notation is actually used because of the following. Here, actually, I'm denoting what sort of random variable I'm considering. If the random variable has the notation capital X, I'm using the notation in the suffix, and small x are the values, different values that the random variable can take at different points of time. And its form will be given by this: 1 by sigma root over 2 pi e to the power minus half x minus mu by sigma whole square. This is the form of the probability function that a normal random variable is going to follow. Okay, and the variable x, these values x will take different values. This variable x is going to take different values from the real line, and hence it is a continuous random variable, because you know that minus infinity infinity, open interval minus infinity infinity is the real line. So it can take any value in this part from this particular real line. And also, this is the first part that I was going to tell you. The second part is that you already know that in binomial probability law, small n was the parameter, small p was the parameter. So I told you that if you know small n and if you know small p, then you can get the idea of the binomial probability law. And in the Poisson probability law, What was the parameter? NP. This quantity was the parameter which we denoted by lambda. Okay. In normal distribution, if you just look at this expression, what you will find is that pi is a constant number. It is an irrational number, but it is constant. It is having some constant value. 2 is a constant number. Square root over pi is constant. Minus half is constant. X is having values from this particular range. It depends upon our favorable events. And exponent of something is also a constant value, is also having a constant value. What is important for finding out this particular expression is the following. We need to know this quantity sigma, and we need to know this quantity mu. If we somehow know about mu and sigma, that means we know about the expression. Okay, so from this we can immediately say that mu and sigma are the parameters of the normal variate, What are the meanings of this mu and sigma? Mu stands for mean. Mu stands for mean of the normal variate, mean of x, which we denote by expectation of x, and sigma stands for standard deviation of x, which we denote by root over variance of x. Okay, so if we know the mean mu and standard deviation sigma or variance sigma square, then we actually know about the probability normal distribution. And remember one thing, when we talk about variance, standard deviation, it is always the positive square root of the variance. Now the figure that I have drawn over here, that this is, you can, in this particular figure, you can imagine this to be the origin, this to be your x-axis. Okay, from this is the real line from where the variable is going to take its values, and this is the function f of x. This is the function f of x, which is having values at different values of x. And this quantity, this particular dot that I am marking over here, this is actually the point mu. This is called mean. Okay, so from this particular figure, we can easily conclude that the normal curve is actually symmetric about mean. And this is another property of the normal curve. And not only this is, if you write it as property 1, the property 2 says the mean, the median, and the mode of the normal curve, they coincide at a single point. So if this is the mean, this is also median, this is also mode. Why is it so? This is mean by definition. This is median because it is dividing the entire curve, entire region into two equal halves. And this is mode because the highest frequency is occurring at this particular point. So this is the highest frequency fx maximum. Okay, so this is, therefore this particular point x equal to mu is equal to mean, median, and mode as well. Okay, and obviously this particular bell curve is symmetric about this line that I have drawn over here, this dotted line. And obviously this normal curve is going to have the property, the continuous probability distribution is following. It is always positive because it is a probability, and the total probability is going to have the value 1 always. And it is not true for only normal curve, it is true for any curve, any probability, be it discrete, be it continuous. Now after this, I'm going to the next phase, how to calculate the probabilities, this type of probability with respect to the problems. Now, As you can see, this particular expression that I have written over here is quite clumsy. And you know that this expression is actually, I mean, whenever we do probabilities in continuous case, we need to integrate something, be it finding about expectation or variance or whatever. We try to integrate the things. So since this particular expression is quite difficult to integrate, okay, so one thing that we can do for to uh, ease our job is to transform the variable capital X into a new variable. So we are going to transform the variable X to a new variable capital Z, and that new variable capital Z will be called standard normal variable. So what we are going to do, the transformation is very simple transformation that we are going to play over here. If we have the knowledge of mean and standard deviation of the normal random variable, suppose capital X is the normal random variable which is having mean mu and standard deviation sigma, then what we can do, we can define capital Z in the following manner. We can write it as capital X minus mu by sigma. In school, when you calculated the arithmetic mean, we often used this type of formula like change of origin and scale. Change of origin and change of scale. In this type of calculation, what you used to do is the following. Suppose you want to transform the variable X into variable Y. So you considered a constant A from the data, and you subtracted this constant from the original variable capital X and divided by another constant, say B. Okay, and this type of transformation that you used to do was called the change of origin and change of scale. When we consider the numerator part, that means the origin is being shifted to A and scale is being changed with respect to B. The same thing has been done over here. Here the origin has been shifted to mu and the scale is set at sigma. So what is happening if I try to draw the figure of that? Initially, this was the normal curve that we had. This is the normal curve that we had, and origin was somewhere lying here. Okay, so my drawing is this drawing is not very good drawing. Let me try to draw it once again. This is the axis, and suppose this was the normal curve with respect to the variable X, and this is the point X equal to mu. This is the origin. Now, when we do this kind of transformation, the figure takes the following shape. This is the, just a minute. Now, this is the vertical axis. This is the horizontal axis. And this point was originally this point, X equal to mu. So I'm writing here X equal to mu. And since you have given it this transformation, the curve will shift its position and will become symmetric about X equal to mu. So this particular point with respect to new transformation capital Z is now becoming origin. So originally it was X equal to mu, now it is becoming Z equal to 0 if Z is my new variable. If I shift the origin to the point of median or mode or mean, then the mathematics becomes easy for us to perform. Okay, and obviously, since my variable is now shifted to now changed to capital Z, so the probability function fx will be changed to f of z, and it will be having some sort of form that I'm going to explain over here. First of all, we need to know what is the expectation of capital Z and variance of capital Z. If we know the expectation of capital Z and variance of capital Z, then we can get the formula for fz. Now let us try to calculate these two things. Expectation of z is nothing but the expectation of the right hand side, x minus mu by sigma. Okay, and you know that standard deviation is the measurement of deviation and it is constant. So this constant 1 by sigma can be taken outside the expectation sign. So we get expectation of x minus mu. And you know that expectation of x minus mu can be written as expectation of x minus, or you can write plus expectation of minus mu if you want. And this is nothing but equals to expectation of x, and this minus can come outside the expectation sign and you get expectation of mu, and mu is mean of the random variable which is also constant. So, and you know that expectation of constant quantity is constant, so we can write it as simply mu. But what is mu? As I told you that mu is the mean of the random variable x, and sigma is the random standard deviation of the random variable capital X. So in place of mu, we can put, or in place of expectation of x, we can put mu. Expectation of the normal random variable is nothing but equals to mu, and therefore we get 0. So what we find is that for the new random variable, which we call as the standard normal variable, the expectation is 0. What about the variance? We know that variance of z by the formula is given by expectation of z square minus expectation of z whole square. Okay, but we have already found what is expectation of z, so it is 0. So variance of z just becomes expectation of z square. So we need to calculate this quantity now. Now expectation of z square means we are going to take square of this quantity, isn't it? And this can be written as expectation of x minus mu whole square by sigma square. Now since 1 by sigma is constant, 1 by sigma square is also constant, and it comes out of the expectation sign, and we get this quantity. Okay, now if you carefully observe, you will see that we can write this quantity as expectation of x minus ex whole square, because ex is mu, so we can write this. But we know that variance of x, the actual definition of variance of x is expectation of x minus ex whole square, which has an operational formula which can be written as the following. This formula that I have written over here is the operational formula for the variance. So variance has actually two formulae. So now we can recognize this quantity. This quantity is nothing but variance of x. So in place of this, we can write vx. But from here, from our assumption, we know the standard deviation of x is sigma. And since standard deviation of x is sigma, variance of x will definitely be sigma squared. And therefore, we get, in place of variance of x, I am writing sigma square. We get sigma square by sigma square, which is equal to 1. So ultimately, from the above calculation, we have found that expectation of z equal to 0 and variance of z is equal to sigma square. Standard deviation of z you can consider to be positive square root of variance of z, which is sigma, and capital Z is given by x minus mu by sigma. So this information that I have found out accordingly. Now I'm going to the next page. I ask all of you to quickly take a screenshot of this particular page. So once I do this calculation, now let us try to find out what will be the probability function with respect to this new random variable. So the With respect to my normal random variable, the probability function was given by 1 by sigma root over 2 pi e to the power minus half x minus mu by sigma whole square. Now, when we transform x to z under this transformation, the probability function now becomes fz small z, and we know that the variance of z is actually now, what is variance of z? That is actually 1, as you can see. Because oh, I have to finish this particular portion is not yet finished. What we have found over here, this is equal to 1. What is this value? This value is expectation of z square, and you know that expectation of z square in this particular case, because it is 0, the expectation of z squared is indeed variance of z. Here only it is happening. So we thus found that variance of z equal to 1, and so in place of sigma we can now put just 1. So see, there will be no sigma. The variance is 1 now, so, and therefore standard deviation is also 1. So only this quantity will remain, 1 upon root over 2 pi e to the power minus half. And you know that since z is equal to capital X minus mu by sigma, so the small z, each value of z will be having of this particular form. So in place of z, in place of this quantity, we are going to put small z, and this is the probability law or probability function that capital Z, the standard normal variable, is going to follow, where z is actually going to have sorry, the the range of z is from minus infinity to plus infinity, because z is also a real number. Z is also a real number. So this is the probability function that we are going to follow over here. Now, there are some area properties that this particular normal random variable or standard normal random variable is following. These area properties that you must know. Area properties are follows. Now, if you ask me whether you are supposed to learn these properties or you have to memorize these properties or not, the answer is yes. These area properties you have to memorize. And since you are doing it for the first time, maybe you can think that it is very difficult to memorize this particular values, but once you keep on practicing it, and as you know, in the subsequent modules, it will keep coming in different forms, in different chapters. So ultimately, when when the actual time comes, when it is required from your end to apply it, you will see that automatically your brain will digest these properties. What are these properties? With respect to the standard normal variable, suppose we want to find the probability that this standard normal variable capital Z is actually taking values within this range from minus 0.745 to plus 0.745. If this is the probability that you want to calculate, you can you have to memorize that this probability is equal to 0.50. Okay, so this is the value that you want to memorize. So I'm writing it in different colors. Then the next property that I'm going to write is the following: probability that capital Z takes values from -1 to +1. This probability is given by 0.6826. Then the third property that you are going to memorize is the following: probability that capital Z lies between -1.96 to +1.96. The probability is given by 0.95. The fourth property, the fourth area property that you are going to remember is the following: if capital Z takes values from -2 to +2, its value is 0.9544. The fifth property is if capital Z is going to take value from minus 2.58 to plus 2.58, its probability is 0.99. And the last one is the following, and the most important one is, I'm putting a star mark over here. If capital Z is going to take the value from minus 3 to plus 3, then the probability is actually 0.9973. So first of all, let me say what these values actually mean. Say, for example, this value, what does it mean? It means that if we have this standard normal variable, capital Z equal to 0, then if I consider this point minus 2 to plus 2 somewhere here, then this particular thing actually means that the total probability, if total probability is, if this particular region contains 100% of the data, this particular portion will contain 95.44% data, 95.44% of the total data. This is the meaning of this point. Now, if I change the value to some other thing, some other point, say for example, if I consider this standard normal curve where capital Z is equal to 0, and suppose this point is minus 3 and this point is plus 3, and if I consider this region, then from this particular expression we can say that this region will contain 99.73% of the total data. Okay, these probability laws can also be expressed in terms of normal random variable. Say for example, if you want to write it in terms of normal random variable, then you can express it in the following manner. Say for example, if I want to write this last property in terms of normal random variable, you can write it in the following manner: mu minus 3 sigma less than capital X less than mu plus 3 sigma. This probability is actually 0.997. If you want to write it in form of normal random variable, it will be mu minus 2.58 sigma less than X less than mu plus 2.58 sigma. This is actually 0.99. This can be written as mu minus 2 sigma less than X less than mu plus 2 sigma, that is equal to 0.9544. This is probability that mu minus 1.96 sigma less than X less than mu plus 1.96 sigma, which is 0.95. If you want to write it in terms of normal random variable, it is mu minus sigma less than X mu plus sigma, which is 0.6826. And lastly, you can consider this to be mu minus 0.745 sigma less than X mu plus 0.745 sigma, which is equal to 0.50. So in terms of normal random variable or in terms of standard normal variable, in both these ways you can express this probability laws. Now, if you ask me why these two are same, because one can be derived from the other. How? you can do, you can subtract. Say for example, if I start with this thing, that mu probability that capital X lies between mu minus 3 sigma mu plus 3 sigma, then we can subtract mu from all the sides. So we can subtract mu from all the sides, mu plus 3 sigma minus 3 sigma, sorry, minus mu, and this becomes probability that minus 3 sigma less than X minus mu less than plus 3 sigma. And then we can divide all the sides by sigma, because sigma is a positive quantity, so the inequality will not change. So we'll get minus 3 sigma by sigma less than x minus mu by sigma less than 3 sigma by sigma. And thus we get minus 3 less than z less than 3. So you see that one particular expression can be derived from the other expression. Now, if you ask me, you can at this particular point you may ask me two questions. First question that you can ask: why should we remember? Why should we remember these probabilities? Can't we calculate? Remember these probabilities. And number two question: how these probabilities have been found? How these are found? So I'm going to reply to these questions. Okay, so first of all, with respect to the standard normal variable, the normal probability law is given by 1 by sigma root 2 pi e to the power minus half x minus mu by sigma whole square. Now, whenever I'm asking you to calculate this probability, okay, it means with respect to the continuous probability law that you are going to integrate the quantity from mu minus sigma to mu plus sigma. That is definite integration that you are going to perform. Okay. Now, as I can see, the time is almost running out, so I'll not be able to continue this discussion in this particular session. So let's continue in the next session. I'm stopping over here right now. Please join in the next session so that we can continue. Okay.